For the last few years, I've been studying a bachelor's degree majoring in maths and music. This tends to get a reaction out of people, since it's a little unusual. They want to ask me why I chose this, what I plan to do with it, that sort of thing. But very often, I get asked about the connections between maths and music. It gets thrown around a lot that people who are good at music are good at maths and vice versa, and I guess people want me to validate that idea. And my answer has always been, no, there's not. Because the actual experience of studying both is very different. In maths, you learn about a wide range of techniques and structures, which you can use to solve problems. One of the main things you look at is something called a function. A function is a map from one set of things to another. You could construct arbitrary maps if you wanted to, but usually we looked at functions which mapped numbers to other numbers, which I can represent visually like this. On the horizontal axis is the number I am putting into my function, and then on the vertical axis is the number my function points to. Once we have a function, we can look at its properties related to other functions and use them to model real-life situations. And so I've learned some techniques about how to do that. Music, on the other hand, is about a certain kind of cultural product. Humans have the ability to detect vibrations in the air created by objects in our environment, which we call sound. We figured out that we could cause sound ourselves, and we found that we like some of them. We created specific objects called instruments, designed to have good sounds, and we put them together into performances. We created traditions about when to play certain sounds rather than others, and we thought about the ways in which you can systematize the sound of a particular aesthetic. And so, through studying music, I've learned how to play my particular instrument of choice well, how others in the past and present have written their pieces of music, and about the ways music has impacted us socially, which is nothing like anything I was doing in maths. I mean, why would you expect my ability to analyze a function to help me keep time? Clearly, these are completely different practices with no significant connections between them. Okay, there is one thing I could think of. I took a class on the aesthetics of music, and we considered the question of why music sounds good. There are a lot of answers to this question, but one way you might tackle it mathematically is something called the Harmonic Series. If you pluck a string, you get a note, called the fundamental. That note is a vibration at a particular frequency. The note you get depends on the vibration of the string. Go figure. But if you look at how a string actually vibrates, it doesn't actually look like this. More often, it looks like this, which is more complicated. To explain this, we need to look at the different modes a string can vibrate in. It can vibrate across the whole string, or across half the string, in thirds, quarters, etc. These modes produce higher frequencies, which are multiples of the fundamental frequency. In reality, a string doesn't just vibrate in one of these modes, it'll vibrate in all of them at once, and so you get this more complicated movement, which is the sum of these different modes. Since we are used to this sound of all these pitches coinciding with the fundamental pitch, these notes sound good together. But I mean, this is a pretty basic connection. All I did here was use maths to describe the physics of a string. This is what maths does. It provides a framework through which to analyze other phenomena. I could just as easily apply this to any other field if I had the requisite understanding. This doesn't speak to an explicit connection between maths and music, nor does it really capture the complexity of maths or music in their own right. Like, okay, let me tell you about something crazy. So the functions I was talking about before, these functions can look crazy depending on how vindictive you want to be. I can keep on throwing up some weird ones and they look pretty unrelated to each other, right? Well, in a second year maths class, the lecturer wrote this on the blackboard, which looks pretty complicated, but was mind-blowing at the time, so I'm going to try and explain it. A sine wave is a particular function that looks like this. It oscillates back and forth between two numbers. If we mess with some of these numbers, we can make it go faster or slower, taller or shorter. This lecturer was saying that any function that we could think of could be described by adding up a bunch of different sine waves in what's called a Fourier series. This was weird, and to be honest, I didn't really get it. I mean, any function I could think of could be represented this way, but I learned the formulas, did the calculations, and I saw that, yes, they did work. Meanwhile, in my music classes, I was dealing with completely different ideas. I was learning about 4-part harmony and how rhythms overlap and the history of music around the world, and... Wait, just hold on a second. These drums have a weird tone in them. Let's just put that on there. It's... there. Okay. Yep, there we go. What was I saying? Oh yeah. Along the way, I also learned about recording music. These days, to record music, we often use a digital audio workstation, or DAW. Sound is recorded as an electronic signal or completely synthesized. It's captured in the DAW, and there we can start doing various manipulations. And when you're first starting out, there's a very steep learning curve. There's the basic stuff about not recording too loud or too soft and how to capture sounds effectively. But even if you have all that, you have all these options when it comes to enhancing or detracting from a sound, and it doesn't really make sense how these things are working and how to get something to sound good. But you give it a shot, you try some things, they don't work, you try again, and hope that you're getting closer to knowing what you're actually doing. So these two subjects were very different from each other, though they both gave me a lot of hassle over the years as I tried to master them. But one never gave me insight into the other, but people kept on asking me to find a connection. And so I just started to get frustrated and jaded by the question. In third year, in a class about using computers to do maths, we revisited the idea of Fourier series. The lecturer asked us, okay, so you know we can do this, we can take any function and represent it this way as a bunch of sine waves. So what? What do we actually learn by doing this? Well, we can look at these numbers, the coefficients in front of these sine waves, and we can think of this number as how important it is to making up this particular function. So by taking this number, representing it like this, which is pretty much the same thing, just trust me on this, we can come up with this, the Fourier transform. This essentially gives us the value of that coefficient for a given frequency. If we take a function and do a Fourier transform to it, it shows us how much of any particular frequency made up that function. We can see, oh, this function was made of this frequency, and this frequency. So, this is cool. But the best thing is, we can do this in reverse. We can take this frequency function, apply the inverse Fourier transform, and get back to the original function. This might seem trivial, but in maths there isn't always an inverse function. And when there is, it's not always easy. But this is just changing a few plus and minus signs. This gives us a way to clean up a function. Like, say our function is a bunch of data, we can remove any noise from the frequency function and just get at the thing that's useful to us. So, in summary, I can take any function, apply a Fourier transform to it, and once I have that, it's under my control. I can amplify or remove aspects in it in order to find the thing I need. Which made sense.